In section 1011, we're looking at rolling motion of rigid objects. We want to be able to explain the rotational concepts connected to rolling motion and describe the position, velocity, and acceleration of points on a rolling object. We're also going to use energy considerations along with the parallel axis theorem to solve some problems involving rolling. Now I want you to notice, first of all, that rolling is not the same thing as spinning. If we were to think about a CD that was simply spinning, and we were to watch a point on the edge of this CD and watch where it were to move, we'd find that it just continues to return to the exact same position over and over and over again as the CD spins. Rolling motion is not that same kind of motion. Notice in the figure that we have above how the center of mass moves through this nice straight line that we notice here. But if we were to watch a point on the rim or the edge of this rolling object, like we were talking about with the CD, it does not move in a nice circular path. Instead, it moves in more of a complex path that we actually call a cycloid. Now, without friction, an object would never roll, because if you pushed it across the surface, it would simply slide across that surface and never begin to roll. So, rolling actually requires friction to take place. In fact, if the friction is large enough, the cylinder would roll without slipping. So, if something is going to roll without slipping across the surface, what kind of friction are we actually talking about? Of course, it would be an F sub S. It would be static friction that we're looking at if we were going to be rolling without any sort of slippage. Now, as the cylinder rotates through some angle theta, if we were to think about this object moving through maybe an angle that we could define here as a theta, as it moves through that theta, the distance that the center of mass would move would simply be the arc length of this section of the circle. And remember, arc length is defined as an r theta. Now, since we would move through that distance of r theta, we could find the velocity of the center of mass by simply taking a derivative with respect to that position or distance over time. R can be pulled out of the derivative since r is not changing for any point along the on the object. And we get this d theta dt, or basically just r omega. So again, the velocity of the center of mass can be thought of as an r omega. And if we do the exact same thing with acceleration, and now take the derivative of r omega with respect to time, of course d omega dt is simply equal to alpha. So the acceleration of the center of mass is simply an r alpha. Now, the translational velocities of various points can be seen in this figure that we have up here, that various points of the circle would move with different velocities. Again, it's just like spinning. If you were at different points along the CD, the outside versus a more inside piece, you'd be moving with different speeds. The same is true of a rolling object. Various positions are going to be moving with different speeds. Notice how, depending on how far away from the rotation point, or the point that's stuck to the ground, notice how different distances from that point will result in different velocities. The points that are farther away from that pivot against the ground will be moving faster, and the points that are closer to that will be moving slower. So these different points, again, you could find their velocities by looking at an r omega. Now, what about the actual contact point P? Right at the point of contact, the spot that's stuck to the ground right here, that spot actually has a zero velocity at any point in time. Essentially, it's like it's stuck to the ground, remember, with static friction. And as it's stuck to the ground with that static friction at any point, the rest of the object is essentially trying to roll over the top of it. If we were to now consider the energy of this rolling object, we would really have to consider two things. We'd have to consider the fact that the center of mass of this wheel is in fact translating. Remember, the object started out with its center of mass being located somewhere around here, and ended up with its center of mass being located around here. So the center of mass is in fact moving, meaning that we would have a 1/2 mv squared for that center of mass translating across the surface. But we would also have a kinetic energy of the object itself rotating and spinning. So there would also be a 1/2 a 1/2 I omega squared. So rolling objects are always going to include two terms for the kinetic energy, both the translational motion of the object moving across a surface and the rotational motion of that spinning and that roll. Now, as we look at this equation that includes both the translational motion and the rotational motion, we can look at this equation and we could actually simplify it a bit more if we wanted to. Certainly this would be one way to consider the motion and to account for both of those energies. But another way to look at this same equation is with something called the parallel axis theorem. In the parallel axis theorem, we can find the moment of inertia through any axis parallel to an axis through the center of mass. Now, when we wrote down this term here of this 1/2 I omega squared, that was the rotational inertia of this object through its center of mass. Basically, the rotation axis was crossing through the center of mass and rotating around that center point. What we're saying is that we could find the moment of inertia through another point, maybe a point on the rim of this wheel. And the parallel axis theorem says that that new moment of inertia would be the original moment of inertia through the center of mass plus an md squared. The d in this equation is equal to the distance from the center of mass to the new axis of rotation, and of course m would just be the total mass of the object. Now we can use this to find the moment of inertia around an axis through the contact point P. Remember, that was a point right at the edge of the wheel. Now, since the distance between the original center of mass axis and the new axis located at the edge of the wheel is simply the radius of the wheel itself, our parallel axis theorem would tell us that the new moment of inertia is equal to the original I through the center of mass plus an mr squared. So, going back to the original kinetic energy equation, we can take these two terms, the 1/2 I omega squared and the 1/2 mv squared, and simply replace v with an r omega. And we would, of course, square those two things. Now we can pull the 1/2 and the omega squared outside, because those things would again be the same for either piece, leaving us inside with this exact value of this I through the center of mass, or the moment of inertia through the center of mass, plus mr squared, which, like we said, is simply just the moment of inertia through that new parallel axis, or the moment of inertia through the contact point P. Essentially what this means is that the kinetic energy of a rolling object could actually be considered to be the equivalent of a purely rotating object where it was rotating around its contact point P. So let's try a rolling motion example together. Here we have a solid sphere. It has mass m and a radius r, and it's going to roll without slipping down an incline at an angle of theta. The incline has a height h and a length x, and we are attempting to calculate the speed of its center of mass once it reaches the bottom of the incline. So we will use energy considerations to solve this problem, knowing that we begin with all potential energy. We start with an mgh, and by the time we get to the bottom of the incline, all of that potential energy has now turned into kinetic. Some of that kinetic energy is the 1/2 mv squared of the center of mass of the object. It is truly translating and moving down the incline. But another bit of that kinetic energy is the kinetic energy associated with the rolling motion and the spinning of this object as it rolls, as it comes down the incline as well. So we can begin to simplify a little bit. We still have an mgh on this side, but we could rewrite our moment of inertia. For a solid sphere, the moment of inertia, again, is 2/5 mr squared. And of course, again, knowing that v is equal to r omega, we could rewrite omega as a v over r. So we'd have a v squared over an r squared. We could simplify a little bit. These 2's would cancel. We could also say that this r squared would cancel out with that r squared, so that we have an mgh equaling a 1/2 mv squared plus a 1/5 mv squared. Our m's could also cancel since there is a mass in each of the terms that we have here. And simplifying even further, we could come up with common denominators where this would be 5/10 and this one would become 2/10, so that we end up with 7/10 v squared. And solving for the v, we now have 10/7 gh on this side, our v squared on the other, and we can now take the square root of both sides to solve for the v. So the velocity of our center of mass of this rolling object, once it reaches the bottom of the incline, would be the square root of 10/7 gh. You could also be asked to find the acceleration of the center of mass of this object. In this case, because this object would be accelerating uniformly, we could actually use our kinematic equations for that, recognizing that vf squared equals vi squared plus 2ad would apply to this problem. Now our final velocity squared would be the 10/7 gh. The initial velocity squared would simply be 0, plus 2 times the acceleration of the center of mass that we're looking for, multiplied by the distance that it moves through, which would be the length x defined on our drawing. So if we were to take the 10/7 dividing by a 2, we would have 5/7 gh, and then divide out the x and solve for our acceleration as well.